things about the speed of sound. So I'm going to scooch this up, and I know, Banan, you just kind of snuck in there, so if you want to just get that from a neighbor, because I just moved it, okay? So the speed of sound, all right? Obviously, wave speed depends on what? Now, I totally know why you said frequency and wavelength, but that is always a tricky thing. I know that if I change frequency and wavelength, yes, that will change the wave speed. But remember what I've been like pounding this into your heads. There's one thing and one thing only that controls the speed of a wave. Wave speed depends on medium. Because when I change my frequency and wavelength, think back to that Wiggler lab when we kind of had the string. As the frequency goes up, right? If V doesn't change, the wavelength must go down because F times lambda has to stay constant, all right? So changing the frequency actually doesn't change the speed. All changing the frequency would do would be changing the wavelength, right? And that's something that many students missed on that test, which brings me to a reminder. Do you guys, positive physics, have you checked it out? I hope that you're doing it because I want you to have that done by Friday. I'm going to close it at Friday midnight for those of you that are worried about it. And if you get it done, 5 points are going on to your test grade, okay? So please remember that. So remember that wave speed depends on the medium, all right? And so let's talk about comparing the speed of sound in a solid to the speed of sound in a liquid to the speed of sound in a gas. All right?
So are we doing the speed of sound as V?
Yeah, V, when I write V, is always the speed. It's the velocity. Does that make sense? And I'm just saying, let's compare the three different normal materials, solids, liquids, and gases. Finhans. From like chemistry, biology, just your sort of run-of-the-mill knowledge here, what do you remember about the structure of a solid? Like, how does it look? If you were to like zoom in and look at a solid, everything's close to each other. So what I'm going to do is I'm going to draw kind of what a solid looks like at an atomic / molecular level here. All right, we do have a little bit of note taking today here, guys, because I want you guys to understand some important things about sound. So the molecules, the atoms, they're really packed together, right? Give me a head nod if you remember that from like chemistry class. Some of you may not remember anything from chemistry class. Right? Now, let's warm it up a little bit, right? When you warm something up, Cal, what happens to the motion of the molecules as the temperature goes up? They what? They do spread out. Do they move faster, slower, or the same speed? They move faster. So as I heat this up, right, as I add some heat, am I still on screen? Yeah, except that I'm blocking it with that. I'm sorry. All right, so if I add some heat, now think about what the molecules, the atoms are going to do. Cal hit the nail on the head. They're going to be a little bit further apart, right? And to indicate their motion, why don't we put some arrows on here? Boom. And they're kind of random, you know. You don't really know which way they're going, which is why when you pour a liquid out on a table, they slide past one another. Those atoms, those molecules, they don't hold on to each other as tightly. So Cal, that was fantastic. Now, Jared, let's add a little bit more heat and let's make this into a gas. Describe what's happening motion-wise and spacing-wise here, buddy. They're moving a lot faster. Are they still the same sort of spacing? Are they further apart? Are they closer together? What would you say? They're further apart. So now what I'm going to literally do is just draw a couple of them. And to indicate that they're moving super fast, how about we do some really long arrows? Does that make sense to all you guys? Give me a head nod. Give me something if that's okay. All right, cool. Now, we're talking about the speed of sound in these three different types of materials, solids versus liquids versus gases. We've already seen that the particles have a different arrangement here. Roy, how are you this morning? Doing okay? I'm going to pester you for a second. All right. These are very rigid and very organized and very structured. You guys know what OCD is, right? If someone's OCD, what does that mean? Do you know? Obsessive compulsive disorder? Do you know what it means? It's okay if you don't. Can we bail them out, help them out? What is it? If someone has OCD, what does that mean? Yeah, go ahead. How many of you have really neat bedrooms at home? Like everything has its place. Super organized. No one's going to admit that. Probably no one actually is like that. All right. OCD people, very structured, very rigid, very organized. If someone has OCD, you come along, you move something, you know what they're going to do? They're like, they're going to put it right back. You know, they do not like disturbances. I like to think of solids. They're like the OCD, right? They are not liking disturbances. So I want you to think about a sound wave. Sound wave comes along here, Roy, pushes on these molecules. Do you think that it likes being disturbed if it's very rigid, very structured, very organized? Nope. So what happens in a solid is that disturbance, they're going to snap right back into place. And so because they snap right back into place, it's kind of like a rubber band, okay? You pull a rubber band, as soon as you let it go, doesn't it snap back into place? Right? So what we say for solids have what we call high elasticity. Okay? When you disturb them, they snap back into place very rapidly. Now, Roy, think about a liquid. Do those particles seem as structured and as organized as the solid? No, they don't, okay? So when you push on a liquid, and you've probably experienced this, you're trying to wipe up a liquid that you spilled on the floor or something, you push on the liquid just slides out of the way, doesn't it? You're like, oh no, come back, right? So when you push on a liquid, the liquid does not have as much desire to snap back into place. That's what elasticity is. It's the ability to snap back into place. So a liquid is going to have sort of medium or moderate elasticity. It sort of wants to snap back, but it's a lot more relaxed. Look at it. It's moving around. It's loosey-goosey. It's like, hey, whatevs. Now let's go to the last one, Roy. Do these gas particles, do they have much organization to them at all? No. So would you say that's a high elasticity or a low elasticity, you guys? Very low elasticity, right? So when we are talking about the speed of sound, right, sound is going to travel the fastest in a solid. Sound is fastest in a solid. And the reason is because of that high elasticity. You disturb the solid, and the solid's like, whoa, I don't like this, and it snaps right back into place. So that disturbance, kabam, right, goes right on through the material, right? Because it travels fast, right? You guys are going to do a little something for me here. Everyone put your ear down on your desk. Like, Jordan's already there. I got you. Make sure your ear is actually on your desk. So put your ear down on your desk, okay? So that you can actually hear the desk. It is cold. It'll feel good on your ear for a second. And then I want you to just make a little knocking sound. Okay? Make a knock on the desk. It should be surprisingly loud, okay, for what you're doing. You're not knocking very hard. Is it surprisingly loud for you, or maybe not so much? I don't know. Especially if you have a hoodie, it's hard to hear through the hoodie. So listen, all right? Sound travels very fast through a solid, y'all. All right? Sound travels sort of fast. So sound is sort of moderately fast. Moderately fast. In a liquid. Which means then we get to the end. By the time I'm looking at a gas, sound is going to travel fastest or slowest here. Look at the pattern. What is it? Not all at once, because the enthusiasm is overwhelming. Thank you. Sound is slowest in a gas. Okay? And I will expect you to know those three things, and I will expect you to know the reason. Do not sit there and say, oh, it's because the particles are all spread out, Mr. Caldwell. It takes a really long time for the particles to hit each other. No, it doesn't. It's when you disturb a gas, the gas is like, what else? Right? The gas literally doesn't give a fig. Okay? These gas particles, they don't interact with each other at all. They're the opposite of OCD. Someone comes along and messes up their papers. You think the gas cares? Nope, it's a gas. Those particles are just going everywhere, okay? They run into stuff. They go whatever. They're like the teenagers of the particle world, right? How many of you have a room like a gas? Everything is just everywhere. It's just a mess. You walk in, your parents are always calling you to clean your room. Raise your hand. You gonna admit it? None of you ever admit anything. Oh my God. Are you wearing underpants? Too personal? Are you wearing a shirt? Let's bring it back. Some of you aren't. Okay, great. I'll go ahead and call down there, and I'll get some security people up here because I have a bunch of naked people in here, all right? Literally no shirts, okay? It's like a Tommy Bahamas cruise or something. Yeah, woo! Oh, dear Lord, what am I going to do with y'all, okay? All right. Speed of sound. Solid versus liquid versus gas. Fastest in a solid, slowest in a gas. Old movie. Any of you guys ever seen Stand By Me? It's a real old movie. Okay, and the story is pointless, I won't tell it. All right, so let's go and talk a little bit more now in detail about our friends, the speed of sound in air. Okay, so we move this down, get a little bit more space, right? So the speed of sound in air, this is what the lab was all about last time, guys. And I gave you a formula. V is equal to 331.3 plus 0.6 T. Ms. Ferrafino, do you remember what the T stood for? Not a bad guess, but not actually correct. Temperature, okay? T is the temperature of the air in degrees Celsius, all right? So, we've talked about how the speed of any wave depends on the medium. And if we're talking specifically about air, the one thing that we really do have the ability to measure, the one thing that really does change the air is the temperature, right? Because when the temperature is hot, those particles are bouncing around. They're moving really fast, right? And so, if the temperature is high, right? Look at the formula. If T is large, what does that do to V, the speed of sound in air? Higher or lower? Just think mathematically. Put in a larger and a larger and a larger number. 331.3 plus 0.6. This number is going to get bigger and bigger and bigger and bigger and bigger. So what's happening to V? Oh, come on. What's it doing? Thank you. V is going to increase with increasing temperature. Right? So hot air, sound actually travels faster, right? So this means real bad news if you ever go to Antarctica and your friend is a polar bear over there, because in Antarctica it's very cold. No! Polar bear! Big amplitude sound wave, right? Because you want to warn your friend, okay? Should I yell with a high-pitched voice because it'll get there faster? Polar bear! Will the sound get there faster if I squeal like a silly boy? No, because it's still air. The only thing that's going to control the speed is the medium. Polar bear! It's really cold. Sound traveling faster, slow. Slow. Your friend dies. Why? Because it's cold. Because you decided to go on a vacation to the Antarctic and you got out of the nice, safe crawler that took you out there. I bet you feel bad about yourselves, right? It's terrible. It's a terrible loss, okay? So look, right? Hot air, right? What's the hottest place you've ever been? Someone been to a hot place, and where was it? Florida? Summertime? That's a hot place, absolutely. Who else has been hot places? Where you been? Holy Moses, hot place. Yes. There's like that narrow little ribbon right along the Nile. And it's kind of like, ooh, comfortable. Holy sweet mother of God, hot. Oh, I'm going back to comfortable. Because it's just this narrow little band where they have the water, right? Were you there in like the summertime? Oh, man. Hottest I've ever experienced was Sevilla, southern Spain. And it got up to about 42 degrees Celsius, which for us Fahrenheit people, 110-ish, 115, I'm sure that was every bit as hot as Egypt. Florida can get that hot. But then people in Florida are like, no, but there's always a breeze. It just cools you right off. I'm like, the F no, it does not. It is hot as stink. You walk outside, and boom, you're instantly coated in sweat. I started teaching in Mississippi, all right? School starts in early August in Mississippi. I taught on the 3rd floor of a building built in 1900 whatever. No air conditioning. After 30 seconds in that classroom, every single person looked like they had a bucket of water dumped on them. Because you're just like, and so like you think it's hard to stay awake right now. Imagine it being 150 freaking degrees, and you got me standing in front of you, and you're just like, oh my God, I didn't know I had sweat glands there. Wow, sweat's coming out of there too, huh? Yeah, it's just that hot and nasty. But the good news, let's say, because it's hot, let's think of an animal we might find in the hot desert. Not a polar bear. How about a rhinoceros? They're dangerous. Near the oasis. Maybe they're on their migration. Brian, I teach physics. I'm not a biology guy, right? So, okay, if you're going to hate on my animal, you get to pick one. Look out! Horned lizard! Okay, I've never in my entire life thought about being mauled by a horned lizard, but maybe it happens. Here's the good news. Is that warning going to get to us quick enough? Yes! Why? Because it's hot. Because it's a horned lizard. And you're like, oh, it was the last one. I just made it extinct. Oh, well. All right. What? Oh, animal lovers, you guys. Come on. We're the top dog. We are the top of the pyramid. Don't we get to kill the animals we want? No. Guys, I literally am just playing with you. Okay, so look. Do you need to know how to use this formula? Yes. If I give you a temperature, here's an example problem. Okay, temperature is 20 degrees Celsius, right? Here's what I want you to do. I've got a frequency of 320 hertz, right? And what I'd like to find out is a couple of things. One, what's the speed of sound? What's the speed of sound? How did you get that? Okay. How about we go ahead and use our formula first off, all right? 331.3 plus 0.6. What would go in for T? 20, okay? And so you throw that into a calculator. Now, it might be the number that you gave me. I don't remember, okay? But I do want to just double check it, right? So a simple math problem, 331.3 plus 0.6 times 20, and 331.3, it's 343.3. That's going to be meters per second, right? Just like we've been doing all of our speed problems up to this point. So it's just some simple math there, y'all. And then for part B is if I've given you the frequency, I should be able to ask you a question, something like, what is the wavelength? Now, how would we solve that, Rakeb? Do you have any idea? If I've given you this, and we've just calculated this, does anything come to mind, hopefully? Okay, because what formula should be useful here? There's another speed formula that we've been using a lot lately. Phone a friend? Someone bail us out. What is it? Go ahead, Charlie.
Frequency times wavelength.
You remember that one, right? From the waves test? That still hasn't gone away. We still have it. So at this point, do I know V? Absolutely. 343.3 meters per second. Which do I know? The frequency or the wavelength here, y'all?
Frequency.
We know the frequency, so we plug it in. 320 hertz. And then we find the wavelength. So Raquel, I think you said divide, right? Yeah. So I don't know if that's what you were thinking or not, but we are going to do division here because to get wavelength by itself, we're going to clearly divide both sides by 320 hertz. And so if I throw that into my calculator, we get an answer something like wavelength, lambda, is equal to 1.07. What units would that be in, y'all? Yeah, because the only thing that looks like a length unit is right there, meters. The hertz and the seconds, they cancel each other out. Okay. All right, that's a lot of me talking, right? Now let me see if that's enough for you guys to do everything. I think it is. All right, so let's do this. Changing gears. Let me stop this. Everybody needs to have at least a computer out. There should be one computer for each pair. Perhaps, Quinn, you can go back and work with Miss Ferrafino. And the three of you guys that are over there that are singletons, why don't you guys kind of conglomerate yourselves together and you guys will just be a super group of three. Everybody needs to have a computer